Okay, so here you see I have written down the Lagrangian density of free complex scalar field. ठीक है? And what is this? It is this thing. And what does this Lagrangian density describe? Basically charged scalar particles. Now we are going to talk about some sort of transformations. Right. Now the first one is global phase transformation. You see phi changing to u phi. Now this is the structure of u. Now did you notice anything over here? So u looks like e to the power I e alpha. But note that here this phi, there is some sort of dependence will be there on some variable, say x mu or whatever. But this u, it does not depend on any variable, no dependence. No dependence on any x mu or any variable, right? So that's why it is known as global phase transformation. Remember, we are talking about fields here, right? So global phase transformation of the field, right? Now let's move forward to from no dependence to dependence on x mu, and that will be local phase transformation. Okay, so see, this is global phase transformation, and now I have written down the local phase transformation, where you see there is phase, and the phase depends on position and space and time coordinate. I have written it in the shortened form over here, and also I have written it like this. So overall the moral is there is no dependence here and there is a dependence on x over here, and this is our local phase transformation. Now let's see how this affects the Lagrangian density. Okay, so here you see I have written down the local phase transformation, right? And now let us concentrate on the Lagrangian density, which I have just written down previously on the blackboard. Now it consists of two terms. This term, derivative of phi star and derivative of phi and phi star phi. Now look into the structure u. So from this structure we see that in this term there will be no change. However, there is a problem if we talk about this term. So let us consider only this term. You see how it changes. So you see there is an additional term because of this. So this is the additional term. So what does this mean? This means that the Lagrangian density of the complex scalar field now is not
invariant,
right under local phase transformation. Previously there was no issue. Why? Because this term there was no dependence, so there was no issue. But now because of this dependence, we are observing that the Lagrangian density is no longer invariant under local phase transformation. Okay. Good. Now, what is the way out? You see, physicists are very clever people. So you see, the problem is this term. Okay. So this term is the problem, as I have already pointed out before, because due to this term we are observing the change in the Lagrangian density, right? Now what we are going to do, one of the ways of resolving this issue is we are now going to replace this derivative by defining a new derivative, and that is known as covariant derivative, this d. Okay, covariant derivative. Now look, how is this derivative defined? This is defined in this particular way. I'll talk about this mu later on. So you see what happens if we define it like this, then you see what happens over here. Now compare these two terms, del mu of phi and d mu of phi x. You see, because of defining in this particular way, we are getting only this term. So this means there is no change, whereas there was a change in this term over here. So by defining the covariant derivative, we are able to get rid of this extra term, and now we are observing no change in the Lagrangian density. Okay. Okay. Now look into this covariant derivative. This term, how it is defined, and what is this mu? Basically, it describes a new vector particle field associated with it, and this has been identified. We have identified it as photon. So if we identify it as photon, then we have to write down the Lagrangian density as the scalar Lagrangian density of electrodynamics, and this is the scalar Lagrangian density of electrodynamics. You see, and this is what? F mu nu, right? And it is written in terms of the vector potential like this, and these are the final forms over here. So you see, what is happening is that previously I talked about local phase transformation, and then we saw that in case of local phase transformation, for the case of complex scalar field, the Lagrangian density doesn't become invariant. Now, one of the ways of making it invariant is introduction of the covariant derivative, and by introducing the covariant derivative, or basically by introducing this vector field, what we have done, so we have done two things basically. You see, two things are happening. First, we are introducing the covariant derivative, and then we are requiring that the field remains, Lagrangian density remains invariant, and as a result what happens is the following. What happens is that there is now, we have introduced interaction between the scalar field and what? And the electromagnetic field. Isn't it interesting? So you see, there is an interaction term over here. So we have introduced the interaction between scalar field and the electromagnetic field by requiring the invariance of Lagrangian density in case of local phase transformation. Fine. So this is more or less the overall story. Okay. So you see, now regarding photon, what we can do is, let us introduce the mass of the photon. So how do we do that? So we have to mass of the photon, so we have to add a term like this to this Lagrangian density, right? Now if you do this, then you will immediately see that this Lagrangian density again doesn't become invariant. So what does this mean? So this means that mass of the photon is not allowed by local phase transformation. Okay? Okay. So now let's start with spinal electrodynamics. And the first thing that we will consider is the Lagrangian density of a free electron, which I have written down over here. Gamma matrices, field, mass of the electron, right? This is quite familiar. Now again, just like the previous case, we are going to talk about first the global phase transformation and later on the local phase transformation. Okay. So first is global phase transformation. You see, no dependent on space-time, no dependent on x, and you can check this for yourself as well, that in case of global phase transformation, the density remains invariant. Okay, and similar to the previous case as well, here in case of local phase transformation, which is this, right, the Lagrangian density doesn't remain invariant, similar to the previous scenario. And just like the previous case, so now we are going to define the covariant derivative, and this is follows the entirely same way, just like the previous case. Now let's see what happens after that. Okay, so now with this definition of the covariant derivative, let us write down the Lagrangian density of quantum electrodynamics, and it is this term over here. right? Now look, I have written it in terms of the covariant derivative, which we have defined in the last expression. Okay. Now let me break it down in terms of del mu and n mu, and then we will get, you see, three terms, 1, 2 and 3, and this third term basically shows the interaction of electrons with photons. Okay. Electron with photon, this interaction, and here I have written down the field equation. Any questions? Okay, so you see this quantum electrodynamics is basically a gauge theory, right? And the gauge group here is the group of the phase transformations you want. Now we have discussed about this in quite detail. Now similarly we can consider a larger group of phase transformations, right? Like SU3, and in that case the gauge theory we will have, just like the quantum electrodynamics, we will have quantum chromodynamics, the theory of strong interaction, and this we will talk about in the next class. Okay.